Operating system controls input-output devices. For this purpose, it issues commands, handles interrupts, handles errors. It provides easy-to-use interface to devices, hopefully device independent. First, we will look at the hardware for input-output, then software. We will emphasize software structure, software structured in layers. Look at disks, also clocks, keyboards and displays. Finally, consider power management. The input-output subsystem is the largest and most complex subsystem in operating systems. Most lines of codes are reserved for input-output. Highest rate of code changes occurs. This is the part where operating system engineers most likely to work. It is difficult to test truly. It is a make or break issue for any system. It has big impact on performance and perception, and bigger impact on acceptability in market. Let's first look at hardware. Electrical engineer's view is that we have chips, wires, power supplies, motors, and all the other physical components that comprise the hardware. On the other hand, the programmer's view is focused at the interface presented to the software. The commands the hardware accepts, the function it carries out, and errors that can be reported back. As input-output devices, we have two types. One is block devices and the other is character devices. In block devices, we have fixed size blocks, each one with its own address. Independent transfers, but in units of blocks, for example, hard disks, Blu-ray disks, USB sticks, etc. Block sizes typically in the range of 512 to 32,768 bytes. The character devices delivers or accepts stream of characters. There is no block structure. These devices are not addressable, does not have any seek operation. For example, printers, network interfaces, and furthermore, the data handled by character devices are not addressable, does not have any seek operation. For example, printers, network interfaces, mice for pointing, etc. are character devices. Some devices do not fit. For example, clocks are not block addressable, do not generate or accept character streams, and they cause interrupts at well-defined intervals. Memory mapped screens and touch screens. Block and character device models are general enough and can be used as a basis for making some of the operating system software dealing with input-output devices independently. The file system, for example, deals just with abstract block devices and leaves the device-dependent part to lower-level software. The input-output devices cover a huge range in speeds. It puts considerable pressure on software to perform well over many orders of magnitude in data rates. For example, the data rate for keyboard is 10 bytes per second, while it is 100 bytes per second for mouse. Or for USB version 2.0, the data rate is 60 megabytes per second. Or for SATA 3 disk drive, we have 600 megabyte per second data rate. And also notice that for USB 3.0, the data rate is 625 megabyte per second. A typical input-output unit may have mechanical component and electronic component, device controller or adapter, has a chip on the motherboard, and a PCB on an expansion slot, and a PCB on an expansion slot such as PCIe, etc. For example, a hard disk might have 10,000 sectors of 512 bytes per track. A serial bit stream comes out starting with a preamble with sector number, cylinder number, and sector size, then 4K bits per sector, and finally a checksum or ECC error correcting code. The controller's job is to convert the serial bit stream into a block of bytes and perform any error correction necessary. Blocks are what are sent from a disk controller. Each controller has a few registers that are used to communicate with the CPU. By writing into these registers, operating system can command the device to deliver data, accept data, switch itself on or off, or perform some other action. By reading from these registers, operating system can learn what the device's state is and whether it is prepared to accept a new command, etc. In addition, many devices have a data buffer that the operating system can read and write. For example, computers display pixels on the screen using a video RAM, just a data buffer available for programs or the operating system to write into. How does the CPU communicate with the control status registers and also with the device of data buffers? We have different solutions. In the first one, we have separate I/O and memory space. We have two addresses for memory and I/O ports. In the second one, memory mapped I/O is used. There is only one address space, both for memory and for I/O devices. And another one is hybrid. We have two address spaces, which is used in 86 family architecture. For this one, notice that if we are using in register port, for the instruction in reg port, CPU can read in control register port and store the result in CPU register reg. For out port reg, in this case, CPU can write into control register port the content of the CPU register reg. In R04, for example, and move R04 are completely different instructions. If in instruction is used with register R0 and the port 4, this reads the content of the I/O port 4 and puts it in R0. However, if move R04 is used, then this instruction reads the contents of memory word 4 and puts it in register R0. Now let's see the details of how does CPU address registers and buffers. If separate I/O and memory space approach is used, then CPU puts read signal on control bus, puts address information on address bus, it puts I/O space or memory space signal on control bus to differentiate between memory or I/O. Then read from memory or I/O space. However, if memory mapped approach is used, then in that case, CPU puts address information on the address bus and let memory and I/O devices compare the addresses with the ranges they serve. The advantages of memory mapped I/O are as follows. There is no need for special instructions to read, write, control status registers. There is no need for special protection to keep users from doing I/O directly. Just don't put I/O memory in user space. An instruction can reference control registers and memory. For example, consider loop test port 4, check if port 4 is 0. branch equal ready. If it is 0, go to ready to this line. This is the label. Branch loop. The label loop is here. Otherwise, continue testing. Here we have a loop. In that loop, port 4 is tested in order to understand if it is 0. Disadvantages of memory mapped I/O appears when caching is used. Caching a device control register can be disastrous. Consider the above code, this one that we considered in the previous page, in the presence of caching. The first reference to port 4 would cause it to be cached. Subsequent references would take the value from the cache and not even ask the device. Then, when the device finally becomes ready, the software has no way of finding out. It loops forever. The solution is perform selective caching on per page basis. So this requires extra complexity on hardware. Another disadvantage is if there is only one address space, then all memory modules and all I/O devices must examine all memory references to see which ones to respond to. In memory mapped I/O, all the addresses produced by CPU goes through the address bus. In part A, a single bus architecture is shown. All memory modules and all I/O devices must examine all memory references to see which ones to respond to. If the computer has a single bus, as in A, having everyone look at every address is straightforward. In part B, a dual bus memory architecture is shown. The trend in modern personal computers is to have a dedicated high-speed memory bus between the CPU and memory. The bus is tailored to optimize memory performance with no compromises for the sake of slow I/O devices. CPU reads and writes of memory go over this high bandwidth bus. This memory port is to allow I/O devices access to memory. Solutions for memory mapped I/O with dual bus structures are as follows. CPU tries memory first. If it doesn't get a response, then it tries I/O device. An alternative is to use a snooping device on memory bus to pass all addresses presented to potentially interested I/O devices. However, for both cases, we need more complicated hardware. Direct memory access. CPU could request data 1 byte at a time from I/O controller. This is a big waste of time, hence use direct memory access, DMA. There is a DMA controller on the motherboard, normally one controller for multiple devices. CPU reads and writes to registers in DMA controller. We have memory address register, byte count register, and also control registers, in which I/O port, direction of transfer, transfer units, byte per word, and number of bytes to transfer in a burst, etc. To explain how DMA works, let us first look at how disk reads occur when DMA is not used. First, the disk controller reads the block, one or more sectors, from the drive serially, bit by bit, until the entire block is in the controller's internal buffer. Next, it computes the checksum to verify that no read errors have occurred. Then, the controller causes an interrupt. When the operating system starts running, it can read the disk block from the controller's buffer, a byte or a word at a time, by executing a loop With each iteration, reading one byte or word from a controller device register and storing it in main memory. However, when DMA used, the procedure is different. Notice that here we have CPU, we have DMA controller, this controller for which we have a buffer, and we have a disk drive. And also here is the main memory. The bus is shown here. In step 1, as shown here, CPU programs the DMA controller. First, the CPU programs the DMA controller by setting its registers so it knows what to transfer where. It also issues a command to the disk controller telling it to read data from the disk into its internal buffer here and verify the checksum. When valid data are in the disk controller's buffer, DMA can begin. In step 2, shown here, the DMA controller initiates the transfer by issuing a read request over the bus to the disk controller, given here. This read request looks like any other read request, and the disk controller doesn't know or care whether it came from the CPU or from a DMA controller. Typically, the memory address to write to is on the bus address lines, so when the disk controller fetches the next word from its internal buffer, it knows where to write it. In step 3, data is transferred from buffer to memory. The write to memory is another standard bus cycle. In step 4, when the write is complete, the disk controller sends an acknowledgement signal to DMA controller, also over the bus. The DMA controller then increments the memory address to use and decrements the byte count. If the byte count is still greater than 0, steps 2 through 4 are repeated until the count reaches 0. At that time, the DMA controller interrupts the CPU to let it know that the data transfer is now complete. When the operating system starts up, it does not have to copy the disk block to memory. It is already there. As the DMA controller modes, we have cycle stealing mode, burst mode, and flyby mode. In cycle stealing mode, the DMA controller requests the transfer of one word and gets it. If the CPU also wants the bus, it has to wait. Transfer goes on word at a time, competing with CPU for bus cycles. Idea is that CPU loses the occasional cycle to the DMA controller. However, if the burst mode is used, the DMA controller tells the device to acquire the bus, issue a series of transfers, then release the bus. DMA controller grabs bus and sends a block. In flyby mode, the DMA controller tells device controller to send word to it instead of memory. This can be used to transfer data between devices. Why to buffer data into controllers? One of the reasons is that the disk controller can do checksum before starting a transfer. If the checksum is incorrect, an error is signaled and no transfer is done. The second reason is that once a disk transfer has started, the bits keep arriving from the disk at a constant rate, whether the controller is ready for them or not. If the controller tried to write data directly to memory, it would have to go over the system bus for each word transferred. If the bus were busy due to some other device using it, for example in burst mode, the controller would have to wait. If the next disk word arrived before the previous one had been stored, the controller would have to store it somewhere else. Another question is DMA really worth it? It does not worth it if CPU is much faster than DMA controller and can do the job faster. It also does not worth it if it does not have too much data to transfer. Here consider a system. We have CPU, we have interrupt controller, and also we have some input-output devices. CPU and interrupt controller is connected through bus. As the input-output devices, we have disk, keyboard, clock, printer, for example. When an I/O device has finished the work given to it, it causes an interrupt, assuming that interrupts have been enabled by the operating system. It does this by asserting a signal on a bus line that it has been assigned. This signal is detected by the interrupt controller chip on the parent board, which then decides what to do. The interrupt controller puts number on address line telling CPU which device wants attention and interrupts CPU. Table interrupt vector points to interrupt service routine. Number on address line acts as an index into interrupt vector. Interrupt vector contains PC program counter, which points to start of service routine. Interrupt service routine acknowledges interrupt, saves information about interrupted program. The information may be saved into a user process stack or kernel stack, or both are possible, but both have problems to be solved. We have two kinds of interrupts, which are precise interrupt and imprecise interrupt. An interrupt that leaves the machine in a well-defined state is called a precise interrupt. Such an interrupt has four properties. 1. The program counter saved in a known place. 2. All instructions before the address pointed by program counter have fully executed. 3. No instruction beyond the address pointed by program counter has been executed. 4. Execution state of instruction at the address pointed by program counter is known. If an interrupt does not meet these requirements, then it is called an imprecise interrupt and makes life most unpleasant for the operating system programmer, who now has to figure out what has happened and what still has to happen. In part A, in this figure, a precise interrupt is shown. Here, the instructions just before the program counter, smaller than the value of the program counter, are fully executed, and none of the instructions after the program counter are executed yet. However, in an imprecise interrupt, different instructions near the program counter are in different stages of completion, with older ones not necessarily more complete than younger ones. For example, here is the value of program counter, and this instruction may be 80% executed, this one 60%, 20%, and this is an instruction stored at a location coming after the value of the program counter is executed more than this one, which is before the value of the program counter. And also this one is executed some more, and this one is executed a little. So with older ones, not necessarily more complete than younger ones. How to process an imprecise interrupt? There is a great difficulty. Either need complicated hardware logic to restart after interrupt, which is available in Pentium processor, or have complicated processing in the operating system.